Is it?
In the sense that S0 is same.
Yeah, that's right. Yeah. So this situation, S0 to S1, we have the fold change, S1 over S0. So that's a two-fold change. And we get some response. Now if we go from S1 to S2, right, we get a new fold change. F2 is S2 over S1. And we get another response. Okay. And now if I take this entire signal and I multiply it by something, I'll get the same curve. So you can either think of each step alone or a combination of two steps like that. And
Okay, but this f is assumed to be some delta function if we're just doing a step or something like that? Or is it
oh, f is not a delta function. It's the f is s of t divided by s0. So you have to start, for this to work, you have to start for a long time at some non-zero signal.
No, but you're taking each one of these steps and you're continuously multiplying by 2. You're not just multiplying once by 2.
Yeah. So how should I say it?
So it's s of t divided by the previous
s
of t minus something.
Okay. So you can either analyze it a two-step input signal divided by the original S0, okay, or let here enough time to adapt. Then forget about what was in the past because we adapted, and now go from S1 to S2, and just solve that problem, and you get the same thing. The point is that you need to have enough time before you start in order for the system to adapt. It has to start from the K has to reach its steady state so that the receptor is sensitive around that point. If you make another step now too early, you won't get precisely the same output. So you have to wait for the system to adapt. That's important.
So we're not taking into account the way that S0 changes. We're just assuming that after a while the new S is going to be the old S.
Exactly. Yeah. I mean, if you want to analyze steps like that in a very simple way. But in general, the theorem, I can make not just steps. I can make any kind of S of t and multiply it by scale, and I get this weird A of t, but it'll be identical. It doesn't have to be steps. Steps are easy sometimes experimentally and also conceptually. Did I answer your question?
Yeah.
Good. Yeah.
You started with scaling variance, and now you're also doing rescaling of scale, so it really looks like, very technical. Like physical phenomena.
Yeah.
The connection, is there a connection?
So the question is there a connection between this and critical phenomena, where near the critical point you have fluctuations on different scales look dissimilar, etc. I'm not aware. Probably is, but I'm not aware. But it's sounds intriguing. Now we can ask, is this the only way, a kind of feedback loop like this, where you have this K here, is this the only circuit that can do fold change detection? And it turns out that it's very difficult actually to find circuits that can do fold change detection. But there is another class of circuits, a different class of circuits that can do fold change detection. And we know this from the second lecture. We know this circuit already. So I'm going to just write down here. So for fold change detection, network motifs, we have this circuit, which I'm going to write down like this. We have a circuit where you have the signal, it affects the activity affects K inhibits K like this. And because of this K appearing in front of the equation, I'm going to put down an autoregulation because it's like K is increasing its own production, you can say. So this, I'm going to just write down these equations like this. This is symbolizes the equations back there. So this is kind of a negative feedback with positive autoregulation. You can say some kind of motif like that. That'll give you, if you write down those equations like that, they'll give you fold change detection. And it turns out there's another circuit that can do it that we already know about. And that is actually the first circuit discovered by in that paper I mentioned by Leah Gontoro. And that is this one. The incoherent type 1 feed-forward loop, where transcription factor, or X, activates Z and activates an inhibitor of Z. I hope you remember the circuit. We talked about a pulse generator. But now we can return to it with a little bit more accurate math and show that in some cases it can give also exact adaptation and fold change detection. And maybe I should say, every circuit that has fold change detection must have exact adaptation. That's subsumed, because if I tell you that this step and this step have to have exactly the same output, it means also that S0 and S1, if I now multiply S0 by 2 and S1 by 2, also must have exactly the same steady state output. So steady state output can't depend on the input signal if you have fold change detection. Fold change detection must have exact adaptation. Because if input S goes to lambda to L times S, the A steady state has to stay the same. That's exact adaptation. But circuits with exact adaptation don't have to have fold change detection. Just like linear integral feedback has exact adaptation, but no fold change detection, because so most circuits you can write down that have exact adaptation don't have fold change detection. Fold change is much more rare. And in a screen of all possible 3 molecule circuits by Miri Adler and Avi Mayo sitting here, there's like 10 to the 6 possible motifs you can write. 0.1% had FCD, but 10% had exact adaptation. And basically, those 0.1% fall into either one of 2 classes, the feed-forward loop or this kind of negative feedback loop with auto-regulation. So those are the 2 possibilities, we think, in general for, yeah?
Shouldn't it be negative auto-regulation?
Negative. K is a K here. It's like if you write down, it's like K A steady state minus K A. So it's like in gene circuits where you had K being degraded, but also activating its own production. So it's kind of a positive autoregulation. If we translate back to the gene expression circuits we worked in the beginning, it's like K is activating its own. The equations are like that, so that's why we write this. So we have this X, Y, and let's see why that works. Why does this work? So it works. Well, it works for some assumptions here. So here there's also K, where Y represses Z. So if we write down the equation, so just to show how this works. So the signal, input signal here, X goes up. Y starts being made. Z goes up, starts being made. But then when Y crosses this threshold, it represses Z. And I claim that we can get exact adaptation. Right? So this is Z steady state, Z steady state. And you get a pulse like that. Yeah? And the equations here are dy dt. I'm just going to write very simple equations. Minus alpha 1 y. So this is production by x and removal, like we did in the first lectures. And dz dt I'm going to write down. So x activates z, and y inhibits z. And you get FCD if we're in a regime where y is much bigger than k. That is to say, when we're not at very low signal, but we already have some signal, and we have some y made. This is y, and it's much bigger than k. And if we assume that, I can approximately erase this k, because y is much bigger than k. So we have this x over y. And x over y is already a clue for fold change detection, because now we can have y normalizing the input signal x. So if we if we solve the steady state, I want to show exact adaptation first of all. Exact adaptation. So if we start for the steady state, dy dt equals 0. So that means that beta 1 x steady state minus alpha 1 y steady state equals 0.
Supposed to be alpha 2z, right?
Alpha 2 times z. Yeah, thanks. Correct. Sorry about that. Then the solution here is that y steady state is beta 1 x steady state divided by alpha 1. So that means that y here, y is proportional to the background input, x steady state, just like k was previously. The steady state, if we go from x0 to x1, this will go like x0 and this will go like x1. So y kind of is proportional to the input signal because it's just produced by it.
Why is the production of y proportional to x? Because x is logic, right?
Right, thanks. Yeah, I made a jump here. X, when we talked about network motifs, I used a logic approximation to make things simple. And here I'm using a more, you can say more realistic kind of
But it
model.
It does have a threshold, right? Even if it's not a logic approximation.
Yeah.
Linear approximation to Michaelis-Menten.
Yeah, it's like a Michaelis-Menten function. It's like typically the rate of production of y looks like a Hill function or Michaelis-Menten function. We're just taking the linear approximation of it. That's a good point to remember that we're now dealing with. I could say the first part of the course we used these logic functions to make things very easy to understand. And now for fold change detection, you need to make a little bit more realistic models in order to get a subtle property like fold change detection that you can't get with kind of yes/no things. That's why, as a teaching approach, I started from the logic functions and now I make it more realistic. Did I answer your questions? No. And then what's z steady state? We want that to return back to the same level. So that's going to be z steady state. So if we want this to equal 0, z steady state is this term divided by alpha 2. Right? So z steady state is beta 2 x steady state over y steady state alpha 2. And that means beta 2 x steady state. And I'm going to plug in this y steady state and you'll see things cancel out. Beta 1 x steady state divided by alpha 1. X steady state cancels out. Yay. Beta 2 alpha 1 divided by alpha 1 2 beta 1. So z steady state is the same. It doesn't depend on the background signal. Why? Because y grows with the background signal and it normalizes out x. So if x grows and y grows by the same amount, z doesn't care. So the background signal, so that's why we have this in this range where y is much bigger than k, we have exact adaptation. And then we also have fold change detection because of the same, you can show by the same rescaling y is y over S0 and x is x, or fold change is x over x0. And you do exactly the same rescaling and you come to the conclusion that this circuit also has fold change detection because of the structure of the equations. Yeah.
How did you guess that term beta 2x over k over y?
How did I guess this term?
Yeah.
That's because there's general conditions we know for fold change detection. I'm going to write it down. And they help you guess that you always have to have an x over y here or something like that.
This is the general form of AND gate with a receptor, with a...
Yeah, I mean, this is a very typical for these kind of biochemical equations where you have x and y binding. It's like basically like a partition function. So you have here typically something like this and something like that up there. But so when y is much bigger than k, you can get it. So it's biochemically feasible. But we also know mathematically the equations have to have a certain form for fold change detection. In particular, this equation needs to have something like x over y in it. And this equation needs to be homogeneous in a way that if you multiply the signal x and y by the same constant, this all multiplies with the same constant. We just write it down mathematically that the general condition for fold change detection is if I have a dynamical system, dy dt is some function of x, y, and z. So we have any kind of function. I have here x is the input and z is the output. And you have some internal variables y that can remember things. So here, this is a general way to write down the dynamics. dz dt is g of x, y, z. Then I get FCD if the following conditions are met. If I multiply the input by L and y by L, then L goes out of F like this. And if I do the same to G, G remains invariant. So you can prove this basically using the rescaling argument. But this gives us a test for any f of g to see if they have fold change detection. But just to see this, what's called homogeneity property. If you multiply x and y by L, does L go out of the function? So for example, if I multiply x and y by L here, I get L times the same function. And if I multiply x and y by L here, L cancels out. So here F becomes L times F, and here G stays G. So that satisfies the homogeneity conditions. And so that way you can screen for fold change detection circuits, which is what Avi and Miri did. And for linear, if this equation is linear, it's necessary and sufficient condition for fold change detection. So we know quite a lot about what circuits can do it, and we can say basically it's a kind of nonlinear negative feedback loop, and this kind of incoherent feed-forward loop are two ways you can get it. And let's see how we're doing. We're doing well. Also here, by the way, this is F. So if I multiply K by L and S by L, they cancel out here. So this thing stays invariant. And if I multiply K by L, L comes out. So it also satisfies the homogeneity condition. So this is just a technical thing if you want to go deeper into this FCD. And in general, you can ask about all kind of, this is kind of a symmetry. It's a symmetry to multiplying the input by a factor. It's a scale invariance. There are other symmetries in biology too. For example, if we don't know if the tiger is going to come from the right or the left, we better have a symmetry of right-left in our sensory systems. 2 ears, 2 eyes, like that, right? That's like built into it. It's a symmetry for right-left symmetry. So there are other kinds of symmetry in the world. So we know, for example, ambient light is going to multiply our signal. We can't, that's physics. If we want to not care about ambient light, we need fold change detection. So if we want to be invariant to the multiplicative unknowable factor, we better have this symmetry reflected in our equations so that they normalize it out. So it's a way that evolution, you can say, learns the symmetry and builds an invariance into the equation. So what other kinds of symmetries are there that we can discover new principles? Almost, you could say, even without knowing any biology, only physics, let's say, I would guess the circuit has to be robust to this property and be able to guess what classes of circuits would appear in biology from first principles. Of course, the way it actually happened was looking in detail at incoherent feed-forward loop and bacterial chemotexts and saying, oh wow, they can do this. The circuits can do this, and then finding the general conditions, etc. Did I explain myself? It's a kind of, you look at the biological detail, you see something, you go to the universal levels, to say, and then you can look at new specific systems and ask, like psychological systems, or I mean, we just did an experiment with Avichai Danon on plant photosynthesis. That it turns out that plants also have a sensory system for light, and they detect low lights just at dawn, like that. They detect relative changes of light in their photosynthesis system, probably to prepare, because high light can be damaging. You make these reactive oxidative species. So plants apparently also have sensory, like this kind of fold change detection for low, medium light levels. And now you can, with this principle, you can ask, is it a feed-forward loop or a feedback loop? And from different properties, we can say, oh, it's got to be a feedback loop because of the way the dynamics look. And then we can say, okay, sorry, it has to, in this case, a feed-forward loop. It has to be a feed-forward. Then we ask, what is the y and x and z here that are at play? And that's like a way to go from general principles to specific circuits. Any questions while you raise?
Sorry, what's
Yeah.
the Y with the thing over?
The what?
The Y map?
This thing? This is the rescaled y divided by the background signal. I didn't go through all the math, but if you use these rescaled variables just like before, you can show that these equations become invariant to the background signal. Any questions or comments? Yeah.
In the previous lecture, you mentioned that bacteria has 4 systems like this.
Yeah.
So what is the connection? Like I assume bacteria have a glucose and another delicious, more delicious attractant that will ignore glucose and go for that.
Yeah. So
My question is, given the attractant,
Yeah.
can I predict that which system is working?
I see. So correctly, you say that E. coli has several kinds of receptors. It can taste, each one can taste several attractants and repellents. So in fact, we have multiple signals. So you can ask, how does fold change detection work with multiple signals? Because you have one propeller. So this is very fascinating. It's not only for bacteria, it's also for our sense of smell, for example, where we can smell thousands of odorants. And now we want to smell a rose. A rose is made of hundreds of odorants coming together. Okay, but on the background of a lot of other smells, and we can say, that's a rose, right? We can tell just a few, and they change together because the little piece of air from the rose comes to us. So all these 100 chemicals, the concentration changes together like that with the air that comes. But on top of the gradients of other smells around, right? So, but we can still say, that's like what's called the binding problem. How can we tell an object made of many different signals? Or psychology, right? We get a raise in our salary, we get married, we have an argument with our best friend, all happening together. But we have just one subjective well-being. So how does it integrate multiply? So there's a principle actually for fold change detection. And you can say it's also incomparable things, like getting a raise in the salary, getting married, things like that are incomparable, right? How can you compare the scale? So here, fold change detection can also help compare the incomparable. And the principle is that if you have simultaneous change in two inputs, S1 and S2, that go into an FCD system. So what I'm saying is you have S1 and S2, they're both sensed by an FCD system, fold change detection, that has a one output. Then the AFT behaves according to the product of the fold changes. So what does that mean? That means that if S1 has fold, let's say two-fold change, and S2 has a three-fold change, then A will respond like as if there was F1 times F2, which is a six-fold change in one input. So what does that mean? You take each input, like your salary, and multiply it by the background, and divide it by the background, you get the fold change. So suppose I have a two-fold change in one input, and a two-fold change in the other input, it'll respond like a four-fold change in a single input. Or if I have a two-fold change, what will happen? I'm asking the class now. What will happen if I have simultaneously a two-fold change in one input and a two-fold drop in the other input? Nothing. So this is a way to compare apples and oranges. You normalize each one by their own background, and you multiply the fold changes. And that's the way it works. And that was shown by Yuval Hart some years ago. I can't remember. And so that bacteria navigating around, basically it senses changes in drops in different sugars, and maybe it changes in drops in different repellents, and has to integrate them. So it uses the relative change. That's, by the way, a prediction that has not yet been tested experimentally. That's a mathematical prediction. Yeah.
Is there two circuits for each of the, like one circuit for each of the signals, or two signals coming into the
Okay.
same?
So this works for two signals coming into the same receptor, yeah, and then goes to QI and motors and so on. Yeah? And if you have the receptors in bacterial chemotaxis work together in these complexes, so sometimes you have two kinds of receptors, and they also all go into the same QI. So this will also work if they're physically attached. And if it's two completely kind of pathways, this won't work. So you need some unity. More generally, you can also get this kind of power laws. If they have different Hill coefficients, you can get also a log linear, what's called response. But generally, it's normalized each signal by its own background. And so that's also interesting to see if that works in psychological systems. And yeah.
So your psychological examples, you're saying that if you both get a raise and get a bonus, you'll be twice as happy about it?
Depends on the fold change. So if I get a raise of 10%, that's a fold change of 1.1. Or a raise of a factor of 2. And then a bonus of a factor of 2, it'll be like a raise of a factor of 4.
It depends if you wait between them.
If you what?
If you wait between
Yeah, the waiting time. Also, let's say if we think this is fold change detection, we now have a way to predict what will happen about the delay between them. Does that make sense to you?
Well, there is that thing in cognitive psychology that, for example, if you get a gift, you'll be happier if it comes divided rather than just one gift. So if I'll give you 2 gifts, you'll be happier.
2 gifts at different times?
Not necessarily,
Oh.
just Rebbe said.
That's interesting. So this fact about psychology will be interesting to see how it fits with this. That's exactly. It gives you kind of a theory now, quantitative theory to test things like that. Yeah, a gain is. There's lots of versions in psychology where a gain, a twofold gain and a twofold loss are perceived differently, and we think that has to do with what you compare to. Twofold gain you compare to what you have, and twofold loss you compare to what you're going to have, and then you can get this psychological fold change. You can now make computations on psychological findings with this, and also get a clue about the circuit. I love this. So it's an open field. And of course, many cells in the body have receptors for multiple signals. That's a typical case in human cells where at once you're buffeted by dozens of cytokines, growth factors, and you have to make sense of how to deal with that. I'm going to end with why is this in the part of robustness. So just to say that if you have a cell with a receptor and it's detecting binding of attractants, and now I have suddenly an increase in 10 binding events per second. Should the cell get excited or not care? So the answer is, it depends. If previously it was a situation where it saw just 1 binding event per second, and now it goes to 10, that's an eyebrow-raising 10-fold increase. But if it saw 1,000 binding events per second, and now it sees 1,010, it's probably a fluctuation, and you shouldn't get excited, right? So you have your input. If the input is low, and you have a certain amount or if your input is high and you have the same amount, you should care, and here you should not care. And FCD allows you to care, to do that, to care here because this is a tenfold, and not care here because this is a 1.01 fold, from 10 to 20, and from 1,000 to 1,010. And therefore, you become robust to small fluctuations in input, where small is relative to the context that you've seen. So it's a way to be robust to the fluctuations. Now, a signal of 1,000 has plus minus square root of 1,000 noise. All systems have at least plus minus 30, right, because of the small molecule number. So that's even more than this 10. So you don't want to respond to every stochastic fluctuation. Otherwise, if you responded to absolute changes, to 10 signaling molecules, you would go respond all the time to this noise. Fold change detection makes you adjust your receptors, open your pupils to be respond to changes, but not any small changes which are on the same scale as the back. Changes are at least, if it's thousands, you want to sense thousands change. If it's tens, you want to sense tens. And that gives you the proportions to the context that you're in. Yeah. All right. So I did promise a song. We're going to end with this. Turn and face the strange changes. All right? Let's take a nice big sigh of relief. See you next week.